This section is called A Decade of Wasted Cores, named after the paper that this section talks about. The paper itself is linked in the lecture notes and is an interesting read if you are so inclined. But this is based on a 2016 research paper that was published exposing serious scheduling problems, and they really did go for a dramatic title by saying A Decade of Wasted Cores. And the authors found in this paper 4 significant bugs in multi-core scheduling, such that there were threads waiting to run even when cores were sitting idle. Okay, that's not good, but how bad is it really? Well, according to what they show in the paper, the performance degradation varies depending on what the exact problem is, but it could be as much as 138 times in the worst case scenario, but performance degradation is more typically 13 to 24%. Okay, even if the 138 times is a corner case that's very rare, the 13 to 24% is a lot. Right, that's performance left on the table. Right? Things we could have been getting and were not. So let's find out what's up with that. So there are 4 different problems, all of which result in the same behavior. Right, cores are left idle, although runnable threads are waiting to execute. Now, I mean, we're not like insane bosses who are like freaked out about, workers having 5 minutes of rest, right? Because there's no customers in the shop right now. So if it's really brief, then it's not a problem, right? If a core is left idle for a short period of time, yes, that can happen. Sometimes it just takes time for the next thing to be ready. And we should recognize also that dealing with that situation takes effort, right? If it goes on for a long time, it's more of an issue. If there are 4 CPUs, each of which is busy, and one thread is waiting in the queue for CPU 0, if the thread in CPU 3 terminates, it may take a moment before the thread that's waiting from CPU 0 to move to CPU 3, but it's not for free, right? It takes some effort on the part of the scheduler. We have to notice the situation, decide to do something about it, and actually carry out the move, and maybe it results in some more cache misses. If the thread is waiting for a very short time, that's probably not worth it, right? It can just wait, what's another second or two, or millisecond or two, I guess I should say. Then it's not a problem, but if the thread is waiting an unreasonably long time, then that's a problem. Right? We don't want that to continue. So recall we just discussed the completely fair scheduler. So hopefully you've got that fresh in your mind when we talk about this. But the completely fair scheduler has multiple run queues, one for each core. And if we take a very simple example where we have 2 cores for which we need to schedule, if CPU 0 has 1 low priority thread and CPU 1 has 3 high priority threads, that's not going the way it should go. We should actually be redistributing the high priority threads so that things not only are balanced, but that priority is respected, right? If we don't do this, the high priority threads are running less somehow than the low priority threads, which is the opposite of what we want. So Linux is going to periodically try to keep the queues balanced. And load balancing is a do-what-you-must kind of situation. It can be expensive, so it can run periodically, but it's not something you would want to do all the time. A completely idle core does trigger immediate load balancing. That's okay, right? It's a problem, we need to do something about it. And if a CPU core is currently idle, well, it's not bad for that CPU core to do load balancing so it has more work to do, right? The work is going to get redistributed, and we're not interrupting an already running task on that CPU because, well, it's idle right now. So yeah, of course we need to give it something to do. Load balancing is, in the absolute simplest approach, and this is what people sometimes do in an ECE 459 assignment that's based around load balancing, is we just take tasks from the busiest core and we assign them to the least busy one, ideally the one that has nothing if there's one that has nothing, but we reassign them, right? That oversimplifies the actual solution because it makes no accommodation for cache locality, non-uniform memory access, any of those things that we've talked about as sort of advanced considerations to maximize performance. So above the level of each core is a larger unit, which is referred to as a scheduling domain. And scheduling domains are grouped. These are logical groupings of the hardware, but they are based on what actual hardware is shared in common between them, right? So if they have level 2 cache in common, we would consider them to be in a group. And then there's a larger group where, say, this is the CPUs that have a level 3 cache in common, and then overall here's everything in the system in total, right? This gives kind of a high-level overview, and it helps the scheduler to make decisions about what to do and where to move things, because if we're moving, say, between things in the scheduling domain that share a level 2 cache, that's less painful than moving things that share nothing. So in this image, we have a few different levels, right? 3 groups are reachable immediately from the first core, CPU 0, shown in the top left of the diagram, in 1 hop, and the rest in 2 hops. So the scheduler will try to avoid duplicating work by making sure that one core is responsible for load balancing within that scheduled domain. This is the lowest numbered core that is idle if one exists. Otherwise, it's the lowest number overall if all of them are busy. And the only way that a core that's not doing something can have some work to do is if it gets woken up. So if a core is busy and it notices there's a lazy one that's sleeping nearby, it will wake it up to send it to do the load balancing. Okay, so there's 4 bugs that cause the problem that we've observed in this system. They are, in order, the Group Imbalance Bug, Scheduling Group Construction Bug, Overload on Wakeup Bug, and the Missing Scheduling Domains Bug. Okay, so let's take a minute to talk about each of those and see why it's a problem. So the Group Imbalance Bug. Cores would steal work from other cores if the average load of the victim scheduling group, the one from which the tasks come, is higher than the average load of the scheduling group doing the stealing. But averages can be misleading, right? If 3 of the 4 CPUs there are maxed out and one of them is idle, whereas over here all of the CPU cores are at 80%, yeah, the average is misleading in this case, right? We shouldn't be stealing work in this case from another group. We should be redistributing work in our own group. Or alternatively, if it's the other way around, we might end up stealing tasks from a group that has an idle CPU. So we don't want that. So averages are misleading. The fix instead is to use the minimum load of the group, which is to say the load of the least loaded core in the group. And this means that cores will steal more often, but we prefer that to leaving them idle. It might mean there's some unnecessary stealing and some extra work is done and some extra cache misses occur as a result of that, but that's still better than just leaving them idle because, yeah, it results in a net performance increase. In the paper, the authors show this can result in a 13% decrease in the runtime of Make. Of course, your mileage will vary. There's going to be different behavior depending on the actual thing that Make is making. But to give some idea of the potential speed up, there's that. The next problem is scheduling group construction. And the task set command in Linux is used to pin applications to specific cores, that is, configure processor affinity. If groups are 2 hops apart, load balancing might not steal them because, well, we expect that there's not enough stuff in common, right? There's no level 3 cache or level 2 cache in common, so we think it's not worth it to steal it. The problem is, in this bug, that all groups are constructed from the perspective of core 0. So that's a little bit like saying if you looked on Google Maps and Google Maps told you the distances to places you wanted to go, but it always used your home address as the starting point. that might be fine if you're actually at home. But if you're not at home right now, like you're at the university and you want to get directions to the supermarket or whatever, getting the distance from home to the supermarket is probably different from the distance from the university to the supermarket. And you might make a wrong decision based on that. Like, oh, it's only 500 meters away, when in actuality it's like 2.5 kilometers away. So if load balancing was running on core 31, it might not steal from a neighbor like core 29 because it thinks it's too far away because core 29 is 2 hops away from core 0. Oops. Third bug, overload on Wakeup. We already discussed processor affinity, and this is an example where too much affinity is a bit of a problem. If a thread goes to sleep on group 1 and it gets unblocked later by another thread, we try to put it back where it was. That's not always what we want. Sometimes what we want is to assign it to, say, a group where there are available cores. Right? Even if other groups are not busy. It reduces the number of cache misses, but it means sometimes a thread gets in a queue that's busy rather than one that's free. This is a little bit like if you're at the supermarket and you're in the checkout line and you realize, oh no, I forgot bananas, and you go back and you get bananas, then you insist on getting into the same line, even if one of the other cashiers has nobody in line. Right? Not great. Doesn't really do what we want. That's not ideal. It would reduce the number of cache misses for sure, but why would you enter a queue that's busy instead of one that's free? And then finally, there was one more bug that appears to have been caused by an error during refactoring. When a core was removed and re-added, some function was no longer invoked. This, I think, is somewhat rare in a typical operating system scenario that we talk about because we don't have cores joining and leaving the party very often, but it was an issue in some of the systems that it was being tested. And this would cause all of the threads in an application to run on a single core, even though other threads were idle, other cores were idle at the time. All of this is to say that in conclusion, scheduling is by no means a solved problem. Right? We've talked about many different scheduling algorithms, and they range from very simple to quite complicated. And as time goes on, the hardware that we're working with changes, and our limiting factors change, and so there's continuously ongoing changes to how the scheduling algorithm works, in the expectation that we can get better and better behavior and adapt to things. The simple scheduling algorithm that worked well in a single core environment doesn't work as well in a multi-core world. Scheduling algorithm that was intended for a time-sharing batch job system isn't necessarily a good match for desktop. And other fun lessons that will hopefully stick with you around other kinds of problems and not just scheduling is, number one, averages can be misleading, and number two, optimizations sometimes do more harm than good. So we have to be careful and check our assumptions. So that's really it in terms of scheduling as a topic. There is a bit of a transition. We're going to talk about I/O devices for a bit, and then we're going to talk about scheduling for I/O devices, just to make sure that we've got all that covered. But this ends the scheduling topic for real as we enter into the last major topic of the course, where we talk about input and output devices.